Hello everyone, I'm Giovanni Tambalo. I'm a postdoc at the Max Planck Institute for Gravitational Physics in Potsdam. And today we will talk about gravitational wave lensing as a probe of dark matter halos. This is a work in progress with Miguel Zumalaccarregui here in Potsdam as well, Yang Dai and Mark Chung. So this is the outline of the presentation. So first of all, I will introduce gravitational lensing and lensing over gravitational waves. Then I will spend a few slides on how we compute lensing signals and what type of lenses we study. And then I will move to a forecast for gravitational wave detectors, in which we establish whether we can probe dark matter properties with lensing of gravitational waves. And then I will apply this to dark matter models. And then I will end with conclusions and outlooks. So we know that gravitational lensing is very important for electromagnetic waves. And it's a very established probe at different scales and provides powerful insights on matter distributions in the universe. And typically, lensing gives us different images of the same source. The same can be applied also to gravitational waves, since they are also affected by the presence of the lens. However, we have some crucial differences that can be very important for applications. So the first one is that gravitational waves, contrary to electromagnetic sources, have a coherence, a phase coherence, and they have much lower frequencies. And moreover, we know how to model the emission of these gravitational waves. Because of the low frequency, we can actually probe, hopefully, the diffraction regime of lensing, which is typically not possible with light. Moreover, we are sensitive to one of the distance because we are measuring the amplitude of the gravitational wave. And also there is no absorption by intervening matter. So we can actually probe dense regions like dark matter cores. So typically in lensing, what we are interested in is this amplification factor, which is defined as the ratio between the lensed signal over the unlensed signal. And the situation usually is as follows. So we have a source with impact parameter y with respect to the lens. And eventually we have also the detector further away. And the waves eventually will be deflected by the lens, and they will take different paths associated to different images. But overall, in the full glory, this amplification factor is given by a diffraction integral of this type, in which we essentially add up all the ways in which the wave can go from the source to the detector. And of course, at the detector, we have to consider that these waves will have different phases. And here are the conventions. So we work with dimensionless units in terms of the Einstein radius of the lens. X is a position in the lens plane, and Y is the impact parameter with respect to the lens. Then this phase phi is often called Fermat potential, and is just essentially the time delay between different paths. It has a component given by the geometry of the system, so it depends on the distance x and y, but also there is a component given by the projected mass distribution of the lens, which is given by this lensing potential psi. Finally, the last component is this factor w, which is a dimensionless version of the frequency rescaled by the lens mass. And as you can see, for gravitational wave frequencies, it can be in a regime in which W is of order 1. And instead for light signals, typically this W is much larger than 1. Okay, so we have also some limits in which we can compute analytically the behavior of F. So the first one is for W much smaller than 1. This limit, essentially the wavelength of the wave is much larger than the size of the lens. So we can imagine that the wave doesn't feel the presence of the lens, and so the amplification is 1. We have no lensing. In the opposite limit, we have W much larger than 1, and we call this limit geometric optics. And in this limit, the diffraction integral is dominated by the stationary points of the exponent here. And this gives us the lens equation, which essentially is an equation for x as a function of the impact parameter, and gives us essentially the position of the images in the lens plane. And associated to each image, we have a magnification, mu, well, it's time delay phi, and a Morse phase, which is just a phase taking into account whether this stationary point is a minimum, a saddle point, or a maximum. And overall, this is the shape of the amplification factor in this limit. However, if we are in an intermediate regime where W is of order 1, we have no analytic control on F, and we have to resort to numerical calculations to obtain the full signal. And this would be the shape that it can take. As you can see, we reach the limit of F equal to 1 at low frequencies, and eventually we approach geometric optics at larger frequencies. But in between, the signal needs to be computed numerically and differs from geometric optics. So standard numerical techniques to compute this F are quite expensive and troublesome because this diffraction integral is highly oscillatory. So what we implement instead is a so-called contour method, first developed in this paper. And this method essentially deals with the time domain signal instead of directly with F. Since for I of tau, it's much easier to get an answer, a full numerical answer. This is because by taking the Fourier transform of our diffraction integral, we are essentially obtaining a Dirac delta that localizes this two-dimensional integral over one dimension and with time delays equal to phi. So we reduce the problem to a one-dimensional integral over contours of constant time delays. And finally, we have also to sum over different paths that are associated to each image. And so overall, we have to compute one-dimensional integral of this type. So this is how it works in practice. So first of all, we have to solve the lens equation in terms of position of the images. And then around each image, we can obtain these contours of equal time delay. And once we have these contours, we can compute I of tau, which is given by this black line. And as you can see, we have these continuities and singularities, which are associated to the presence of the images. And on top of this, we have some smooth contributions that eventually are related to the wave optics regime of the diffraction integral. And once we have I of tau, we can then go back performing a Fourier transform to the amplification factor. Okay, so we're interested in lens models actually that can describe dark matter. And what we would like to test is whether gravitational waves can probe dark matter features. So typically what people have studied in the past are lenses that describe dark matter halos with a singular profile, usually going by the name of the singular isothermal sphere, which the density of the halo goes like 1 over r squared, and is characterized by the velocity dispersion. This type of lenses give actually two images, one associated to a minimum and one to a saddle point of the time delays. But we are interested in models that deform this profile. For instance, we are interested in modeling why, whether or not dark matter halos have a core or not. So what we do is to study this modified isothermal sphere in which we had a core, as you can see here. And we can also obtain an analytic form for the lensing potential, where this XC is a rescaled version of this core size, RC. And an interesting feature of this lens is that it's not singular at the origin. And so it provides actually a new image, a new central image with a finite magnification. And this can be interesting to probe models of dark matter, like fuzzy dark matter, that predicts core. So lensing of gravitational waves in general is a quite studied in the recent year subject. And there are current searches for gravitational waves lensed events in LIGO. And there were also previous studies on mainly on singular lenses for future detectors like LISA. And as I said, what we're interested in is understanding whether we can probe the presence of a core with LISA and also with LIGO. So to do so, we perform a Fisher matrix forecast, in which our aim is to understand what are the sensitivities on the lens parameters once we detect a lensed event, for instance, in LISA. And we perform a simplified analysis in which we reduce the number of parameters of the source, but we take into account the lens parameter, like the mass of the lens, the impact parameter, and the core size. So we have these simplified assumptions in which we don't consider, for instance, the spin or the orientation, but these can be details that can be added later in a more realistic analysis, going beyond, for instance, the Fisher matrix approach. Also, we focus on the strong lensing regime, which is the regime in which we have multiple images, so that we can better probe the core size. So this is typically what happens for lensed signals in LISA. So this is the noise curve of LISA, and these are different types of events with different masses of the binary black hole. So as you can see, in these solid lines, we have the lensed signal, and for very high masses, we have barely any effect. But as we increase, actually decrease the source mass, we start seeing oscillations due to the lensing oscillations due to the different images. And this is because for lower masses, we are increasing the value essentially of this dimensionless frequency W. And so we approach the geometric optics regime where lensing features are more prominent. And of course, lens signals typically have different SNRs depending on the other parameters. So these are the results that we obtain for the sensitivities on the lens parameters by varying the source mass and also the lens mass. So as we can see, for instance, we can focus on the sensitivity on the core size. So we can see that for very high lens masses, all curves approach a plateau here, where we have a maximum sensitivity. But all the constraints eventually degrade as we decrease the lens mass. But this is due to the fact that for lower masses, we go to the regime where there is no lensing, and so we cannot really extract the parameters of the lens. And as you can see, there is a similar behavior as we change the source masses. And as I said before, this is due to the fact that for larger source masses, we are, again, in the regime where there is no lensing. So we degrade our constraints. And the interesting result is that given a fiducial value, for instance, of 10 to the minus 2 for the core size, we can actually be sensitive to differences of the order of 10 to the minus 3. So we can really probe the presence of the core with a fairly good accuracy. And here is also a panel with the results for the forecast for different impact parameters. And the trend is similar as before. And the only difference is that you can see that fixed SNR for all these signals, the actually the precision increases as we increase the impact parameter. And this is due to the fact that the central image actually has a larger magnification as we increase the impact parameter. Okay, so at this point, I can draw up some conclusions and provide some future possible constraints on models of dark matter based on these results. So typically models of light dark matter, they predict the presence of cores, and the size of the core is actually bounded by essentially this relation, and also the mass. So we have a minimum size of the core and a minimum mass of the halo. That depends eventually on the action mass. So by using this forecast that we use, we can see what is the forecast on the mass of the dark matter particle if we don't measure any feature associated with the presence of a core in a lensed gravitational wave event. So here are the results for LIGO and LISA for these parameters of the event. And as we can see, so if we measure, for instance, a lensed event with a lens mass of the order of 10 to the 7, we would be able to constrain the action mass below, let's say, 10 to the minus 22. And these constraints can also apply to different lens masses and configurations. Okay, so this was the main results of our work, and what we would like to do next is to extend this analysis also to the weak lensing regime, in which we have a single image. But the interesting thing is that with wave optic effects, we can actually get more information. We can get more information on the lens model. So this is something we would like to explore. Another direction is also to include more gravitational wave source parameters and also include more realistic configurations. So by including, for instance, the LIGO and LISA antenna patterns. So to provide a more robust forecast for lensing events. And finally, we would like also to study more complicated lens models and configurations and see how gravitational waves can help us in this direction. So thank you for your attention, and I hope to answer your questions in the live discussion.